Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last session we were discussing about the phase sequence of 3-phase circuits. So, we will continue our discussion from that point onwards, and let us see what we were discussing about the phase sequence for 3-phase voltage source. Basically when we talk about the 3-phase voltage source phase sequence, we see there are two possible combinations of phase sequencing. In first sequence we discussed that we call it as ABC or positive sequence, where the reference voltage phasor, that is VAN, is leading VBN by 120 degree, and VBN is leading VCN by again 120 degree. So, what we can write VAN as the RMS value of the phasor angle 0 degree, and then VBN will be VP angle minus 120 degree. So, when we say it is balanced, means you will have same magnitude and the angle difference will be exactly 120 degree. So, in that case VBN will become VP angle minus 120 degree and VCN will become VP angle minus 240 degree, or you can say VP angle 120 degree. So, in that case if you see ABC sequence is rotating in counterclockwise and it is in the direction of the rotation of the rotor of the generator. Now, next possible combination is say ACB sequence, which is called as a negative sequence. So, in that case what happens, that your reference phasor, that is VAN, is leading VCN by 120 degree, and then VCN is leading VBN by another 120 degree. So, what we write mathematically, we write VAN is nothing but VP angle 0 degree, VP is the RMS value of the voltage, VCN is VP angle minus 120 degree, and VBN will be VP angle minus 240 degree, or you can write VP angle 120 degree. So, now in that case if you see the phase sequence ABC will rotate in this direction, which will be opposite to the direction of the rotation of the rotor. Now, like the generator connection which we discussed previously, 3-phase load can also be either your Y connected, or you can say star connected or delta connected, and it depends upon what type of end application you have related to that particular load. So, in the case of Y connected, you will have the load components connected in a star combination with neutral. It may be available or may not be available. It is not necessary that you will always have neutral physically present and reachable for connections. So, here you might have 3-phase 3-wire system for the load, or you can have 3-phase 4-wire system for the load. Now, next combination is delta connected. So, this is basically the delta connected configuration. Here you will see A, B, C are connected in triangular fashion, and your phase A, B, C is taken out from the load. So, and if you see this particular arrangement, in this particular arrangement you cannot take the neutral connection out, because it is topologically impossible to take the neutral connection from the delta connected load. Now, whether it is star connected or delta connected, we will say that if it is unbalanced, then the phase impedance will not be equal and the phase sequence will also be out of phase. So, you will have the magnitude as well as phase, both either of two will be out of phase, or you can have magnitude as well as phase both out of phase. So, when you say the load is balanced, it means that phase impedances in all three legs of the load are equal, and in phase means you will have equally connected with respect to phase. So, in case of balanced star connected or Y connected load, you will have Z1, Z2, Z3 all same. So, you will have Zy. So, Zy is nothing but a phasor quantity. So, you will see the magnitude as well as phase both are same in all the three legs. In case of balanced delta connection, you will have Za, Zb, Zc all three same. So, you can say simply as Z delta. So, for star connected we will specify individual legs impedance as Zy. In case of delta connected we will specify as Z delta. Now, we have already discussed the star delta transformation in our previous lectures. So, taking reference of the star delta transformation, we earlier proved that in case of Z delta the value will be equally 3 of Zy when you convert delta connected network into star connected network. Similarly, Zy will be 1 upon 3 of Z delta if you convert a star connected load into delta connected load. So, we can say that the star connected or Y connected load can be transformed into delta connected load or vice versa with the help of the star delta transformation which we discussed earlier. Now, since you can have source and load both three phase connected in either star or delta connected fashion. So, we can have now 4 possible combinations of the connections between source and load. So, we can say source and load are star connected or Y connected, that means the source is Y connected as well as load is also Y connected. Star delta or Y delta combination means the source is Y connected and load is delta connected. Delta delta connection means source is delta connected as well as load is also delta connected. Delta star combination where you will have source as delta connected and the load as Y connected. Now, it is important to note here that the balanced delta connected load is more common in the network than the balanced Y connected load, because it is easy with the delta connected load that you can add or remove the load from each phase of the delta connected load. It is difficult in case of Y connected or star connected, because it is not always possible to have neutral connection accessible from outside for the connections. So, that is why the balanced delta connected load is more feasible for reconfiguring or taking any leg out or doing the changes in the delta connected load. But on the other hand, you will not see delta connected source as a common practice, because if you have the delta connected source, you will see the circulating current, because delta will create a delta mesh which will cause a current to circulate within the delta network of the source, and this will be because of any slight unbalance in the voltages of the three phases. So, because of this you will have circulating current, and this will cause the overheating of the coils of the generator. So, that is why we generally avoid the delta connected source. Now, let us take one example in which we need to determine the phase sequence of the set of voltages, like VAN is equal to 200 cos omega t plus 10, VBN is given as 200 cos omega t minus 230 and VCN is given 200 cos omega t minus 110. So, what we have to do first? First we will convert it into phasors. So, VAN can be written as 200 angle 10 degree, VBN can be written as 200 angle 230 degree, VCN can be written as 200 angle 110 degree. Now, if you see from the phasor notation, you will see that VAN leads VCN by 120 degree and VCN again will lead VBN by 120 degree. So, VAN is leading VCN by 120 degree because 110 minus 10 minus 110 will become 120 and then VCN will lead VBN by again 120 degree, minus 110 minus of minus 230 will be giving you again 120 degree. So, with this sequence you can simply say that the given voltage is in ACB sequence. Now, let us talk about the connections. We saw that there are four possible combinations, that is Y delta, delta delta and delta Y connections between source and load. So, we will first start with Y connection for the source and load. Why we are starting with Y connection? Because any balanced 3-phase system can be reduced to a Y system with the help of star delta transformation. So, therefore, this system is considered as a key to solve the all balanced 3-phase system. Now, a balanced 3-phase Y system is a 3-phase system with balanced Y connected source and balanced Y connected load. Now, let us consider 3-phase 4-wire Y connected system where star or Y connected load is connected to star connected source. So, how it will look like? If you see this particular figure, the source is Y connected, VAN is connected to the A phase of the load through internal resistance or internal impedance of the source. So, we will call it as a source impedance and then you will have transmission line impedance and then the load impedance. So, now the phase A of the source is connected to phase A of the load through transmission line. Similarly, phase B of the source is connected to phase B of the load through the transmission line and then phase C of the load is connected to phase C of the source through the transmission line. And now, the neutrals of both of the source as well as load are connected through wire having impedance equal to Zn. So, now you can see this particular combination is 3-phase 4-wire arrangement where the source impedance as well as the transmission line impedance is considered for the analysis. Now, since these three are in series, ZS and ZL and the load impedance Z capital L, you can club all of them as ZY is equal to ZS plus Z small l plus Z capital L, where ZS is the internal impedance of the phase winding of the generator, ZL is the impedance of the line joining the phase of source to the phase of load, Z capital L is the impedance of the each phase of the load and Zn we have considered as a impedance of the neutral line. Now, in the power system network, the ZS and ZL are often very small as compared to ZL. So, we can assume ZY is almost equal to ZL even if no source or line impedance is given in the question. In any event, by lumping the impedance together, the YY system can be simplified to that. We have to that circuit which we have shown in the next slide. So, if you see in this case what we have done, we have simplified the arrangement which we saw in the previous slide, and we lumped the ZS, Z small l for transmission line and the load impedance to a impedance called ZY. So, now it is much simplified and easy to understand. Now, you can say that both phases of source and load are connected. A is connected to A, B is connected to B of the load, C is connected to C of the load. Now, let us assume that the current which is flowing in the line connecting phase A of the source to load is IA. Similarly, the line connecting phase B of the source to phase B of the load is IB, and line connecting C phase of the source to C phase of the load as IC. We will also assume there is some current IN which is flowing in the neutral wire connecting neutral of the source to neutral of the load. So, now let us see, because let us see the values of the voltage sources. Since we have assumed the positive sequence, the phase voltage, or we also say its line to neutral voltage, can be given as VAN. You can write VP angle 0. So, it is a RMS value. VBN is VP angle minus 120 degree. VCN is VP angle 120 degree. So, this is what you have got in relationship with the voltages for positive sequence phase combination. Now, if we are asked to find the line to line voltage, or you say simply the line voltage would be VAB, VBC or VCA. That means the voltage between A phase and B phase. So, this will be your VAB. Then similarly, the voltage between B and C is the VBC, and similarly again the between C and A will be VCA. So, now we need to find out the value of the line to line voltage, or we simply say the line voltage. VAB you can write as VAN plus VNB. So, if you see this figure, VAB is nothing but VAN plus VNB. So, what you can write? You can say plus VNB or minus of VBN. Now, if you convert both of the voltages into phasor, VAN is VP angle 0 degree and the VBN will be VP angle minus 120 degree. So, this is what we written in this context of ABC phase sequence. Now, if you simplify VAB as VP angle 0 minus VP angle minus 120 degree, you put them into rectangular format, you will get VP. You can take VP out, then angle 0 will give you simply 1, then VP angle minus 120 degree is nothing but VP angle 240 degree. So, when you arrange this particular component in rectangular, so this will be like 180 degree plus 60 degree. Then when you simplify, cos 60 will become 1 by 2 and sin 30 will become root 3 by 2, and since both in the third quadrant you will have minus sign in cos and sin both, and since minus is again in the outer side of the VBN, so you will simply get minus 1 by 2 as plus 1 by 2 and minus root 3 by 2 will become plus root 3 by 2. So, you will get this as a rectangular output of VP angle 0 minus VP angle minus 120 degree. Let us take root 3 as root 3 out from this particular expression. So, root 3 VP will be out, and then inside we are left with only what you can write, this is root 3 V p. So, you will left with only root 3 by 2 plus j into 1 by 2, and this is what you will get the angle as 30 degree. So, V A B will be now root 3 V p angle 30 degree. Similarly, for V B C you can write as root 3 V p minus 90 degree, V C A will become root 3 V p minus 210 degree. Now, if you see V A B, V B C, V C A, V A B is leading V A phase by 30 degree, and similarly V B C will be leading V B by minus by 30 degree, and V C by 240 degree by again 30 degree. So, in the line voltage you will see that these are leading with respect to their phase voltage by 30 degree. So, we also see that the line voltage is now root 3 times of the phase voltage in magnitude. So, how we can write, how we can present in the phasor format. So, you can see for V A B, V A N is the reference voltage phasor, V B N you can take negative of that. So, minus V B N will be in this direction, and then when you sum up these two phasors you will get V A B. So, this particular phasor V A B is leading V A N by 30 degree. Similarly, V B C is also leading by 30 degree to V B N, and V C A is also leading by 30 degree to V C N. So, you can see that the line voltage is leading the respective phase by 30 degree. Now, if you apply KVL to each phase, what you can write? The value of I A, that is the current which is flowing on the line connecting phase A of the generator to phase A of the load, you can simply write I A is nothing but V A N by Z Y. Now, since we are talking about the balanced system, we can conveniently write like this. In case of unbalanced, we cannot write like this, that we will discuss in the later sessions why we cannot write like this. Just for the balanced system, we say that I A is equal to V A N by Z Y. I B you can write V B N by Z Y, while V B N is nothing but V A N angle minus 120 degree. So, you can again write V B is nothing but I A angle minus 120 degree. Now, here I A is the phasor quantity. So, the angle of current I A with respect to V A will be depending upon the phasor value of Z Y. So, in the analysis we have to be very careful about the phasor value of Z Y, so that we get the proper value of I A in phasor terms with respect to V A. So, I B will be I A angle minus 120 degree. So, if it is I A phasor equal to, if you have magnitude angle say theta, then I B will be you get theta minus 120 degree, and I C will be theta minus 240 degree. So, you can see that I A and I A in both of the cases, that is I B is I A angle minus 120 degree. So, I A is the phasor quantity here, and similarly I C is I A angle minus 240 degree. Now, if you sum up I A, I B, I C, you will get I A plus I B plus I C equal to 0, which you can see from the phasor. Since the system is balanced, so all three phasor will sum up to the value equal to 0. Now, what is the neutral current? So, in the figure if you see, neutral current is nothing but the, if you apply Kirchhoff current law at this node, you will come to know IA plus IB plus IC plus IN equal to 0. So, what you can write, IN is equal to minus of IA plus IB plus IC. Now, since IA plus IB plus IC is equal to 0, your neutral current will also be 0. So, in that case, the voltage difference between source neutral to load neutral will be equal to 0, because there is no current flowing. So, therefore, the voltage across the neutral wire will be 0. So, neutral line can thus be removed, because since there is no current flowing, you can remove the neutral wire, and this is economically very important to understand that if the system is completely balanced, the neutral wire is not required, and we can save cost of laying the neutral wire from source to load. So, in a long distance power transmission, the conductors we use are in multiple of 3, because we are talking about the 3-phase system. So, the conductors will be in multiple of 3, and earth will act as a neutral conductor. Now, power system is designed in the way that the system is well grounded at all critical point. Why? Because we want to ensure the safety of the system as well as the person who work on the power system network. Now, while the line current is the current in each line, the phase current is also same in this case, because phase current is the current in each phase of the source or load. And when we talk about the YY connected system, we will see that the line current is same as the phase current. So, what we will do, we will use single subscript for line current. We will not write as IAA, we will simply write as IA for the line current, because it is understood that we are talking about the current which is flowing from source to load. So, that is why we drop the second subscript and we simply write as IA. Now, alternative way of analyzing the balanced star star system is to convert it into per phase, because the system is completely balanced. You can convert the 3-phase system to its equivalent single phase system. So, when you convert the 3-phase system which we are discussing, then you get the equivalent circuit as shown in the slide. Here the VAN, that is phase voltage, is connected to the load ZY through the line. So, one is line connecting between phase A to A of the source and load, and then another line is for connection between neutrals of the source and load. So, this will be a single phase equivalent of the 3-phase YY connected system which we discussed. So, in this case again you can see from the figure that IA is nothing but VAN by ZY. So, we use phase sequence to obtain the other line currents, because we know that the phase sequence is ABC. So, we can easily find out the values of IB and IC with the help of current IA which we have got from its single phase equivalent. So, as long as the system is balanced, we need only analysis in case of single phase equivalent. So, we may do so even if the neutral line is absent, because you can say that neutral is virtually connected for creating the single phase equivalent. Now, let us take one example before closing our today's session. We have 3-wire star star connected system which is given in the figure. So, we have source completely balanced, 110 angle 0 degree, 110 minus 120, 110 minus 240 degree volt as the phase voltages. Line impedance is 5 minus J2 in all the 3 phases, and load impedance is 10 plus J8 ohm. So, you will see that the load is also star connected and it is connected to the star connected source. We have we are not connecting the neutrals because system is balanced. So, what we will do? We will first create its single phase equivalent. So, when you create single phase equivalent, what you get? You will get the voltage source 110 angle 0, and then you will have impedance 5 minus J2, and then again the load impedance 10 plus J8. So, this will be your single phase equivalent of this circuit. So, what will be the value of IA? IA you can simply get, that is 110 angle 0 divided by, you need to just sum it up. So, this will become 15 plus J6. So, you get the value of ZY as 15 plus J6. IA you can calculate now. So, this will become 6.81 angle minus 21.8 degree ampere. Now, since the source voltage are in positive sequence, the line currents will also be in positive sequence. So, IB you can calculate as IA angle minus 120 degree, IA is given 6.81 minus 21.8. So, your IB will now become 6.81 angle minus 141.8 degree. Similarly, IC will become 6.81 angle 98.2 degree. So, with this we can close our today's session, in which we discussed mostly about the Y connected balanced system. So, in next session we will discuss about star delta, or you can say Y delta connected system. Thank you.